Quantum entanglement. Albert Einstein famously called it spooky action at a distance. It's a concept that sounds like it was lifted straight from science fiction. Imagine two particles born together, their fates forever intertwined, no matter how far apart you pull them, whether they're in the same room or on opposite sides of the galaxy. A measurement on one instantly influences the other. If one particle is spinning up, its partner will instantly be found to be spinning down. This bizarre connection, which defies our everyday intuition about cause and effect, isn't just a theory. It's a cornerstone of quantum mechanics, proven time and time again in labs around the world. For decades, however, while we knew this spooky connection was real, we didn't have a complete rulebook for it, especially when things get complicated. Now, that's changing. A team of theoretical physicists has unveiled what appears to be a universal law of entanglement, a fundamental principle that applies not just to simple pairs of particles, but to complex systems across all dimensions of spacetime. This isn't just a minor update to a textbook. It's a discovery that reshapes our understanding of the fabric of reality itself and could unlock the next generation of technology. The classic example of entanglement always involves just two particles, like a pair of photons or electrons. Their properties like spin or polarization are linked. This non-local correlation is the engine behind quantum computing, ultra-secure quantum cryptography, and sensors with unbelievable precision. But the real world is messy. The universe we live in isn't a simple one-dimensional line. We have three spatial dimensions plus time. And quantum systems aren't just two lonely particles. They can be a swirling web of thousands, millions, or even more particles, all interacting. Understanding how entanglement works in these many-body and higher-dimensional systems has been one of the biggest challenges in physics. Most of our solid theories were confined to simplified one-dimensional worlds. The rules for our own three-dimensional universe were largely educated guesses. This is where we need to be clear about the word dimensions. In one sense, you can have high-dimensional entanglement with single particles. A standard quantum bit, or qubit, has two states, like a switch that's either 0 or 1. But a qubit can have 3, 4, or more states, adding a layer of complexity. However, the new universal rule we're talking about today refers to something even more fundamental: the dimensions of spacetime itself. The difference between a universe with one spatial dimension plus time versus our universe with three spatial dimensions plus time. Finding a single law for entanglement that works flawlessly across all these different dimensional frameworks is a monumental leap. It's the difference between having a specific recipe for baking a cake in one specific oven and discovering the universal laws of chemistry that govern how all ingredients interact at any temperature or pressure. The breakthrough came from a team of theoretical physicists led by Associate Professor Yuya Kusuki at Kyushu University's Institute for Advanced Study. Their work, published in the prestigious journal Physical Review Letters, took a tool from a completely different area of physics, thermal physics, and applied it to the problem of quantum information. It's a bit like using a telescope designed to study stars to suddenly see the intricate structure of a living cell. It's a novel approach that yielded spectacular results. At the core of their work is a mathematical quantity called Reni entropy. You can think of entropy as a measure of disorder, or, in the world of information, a measure of uncertainty. Reni entropy is a powerful generalization of this concept that allows physicists to quantify the complexity and information content of a quantum system, essentially to measure just how entangled it is. Using the sophisticated mathematics of what's called thermal effective theory, Professor Kusuki's team derived universal formulas that describe how this Reni entropy behaves. And here is the crucial part: their formulas don't just work for the simple, well-understood one-dimensional systems. They hold true for any number of spacetime dimensions. They had found a universal rulebook. It's like discovering a Rosetta Stone for quantum correlations, allowing us to translate the tangled, seemingly chaotic language of complex entanglement into a consistent and predictable mathematical grammar. This moves entanglement from the realm of strange, case-by-case phenomena into a unified, predictable pillar of physics. So why is having a universal rule for entanglement such a game changer? The implications are profound, touching nearly every frontier of modern science. Let's start with technology, specifically quantum computing. A quantum computer's incredible power comes from its ability to manage and exploit the entangled states of a vast number of qubits. The challenge is that these states are fragile and mind-bogglingly complex to control. It's like trying to conduct a million-piece orchestra, where every musician instantly reacts to every other musician's every move. A universal rule for how entanglement behaves provides the sheet music for this chaotic orchestra. It gives engineers a fundamental design blueprint for building more robust and efficient quantum processors. It can drastically improve our ability to simulate quantum systems on classical computers, and more importantly, it can help develop new, more powerful error correction codes. Errors are the bane of quantum computing. The slightest disturbance from the outside world can cause the whole system to decohere and lose its quantum magic. A deeper, universal understanding of entanglement structure is a direct path to fighting that problem, and it could be a key that finally unlocks large-scale, fault-tolerant quantum computers. But the implications go far beyond building better machines. They reach into the deepest questions about the nature of reality itself. Entanglement isn't just some tool for technology. It's woven into the very fabric of spacetime. This new universal rule allows physicists to explore something called the entanglement spectrum. This spectrum is a detailed fingerprint of how information is distributed within a quantum system. Understanding it gives us a much clearer picture of the relationship between quantum mechanics and gravity. For example, one of the most stubborn puzzles in physics is the black hole information paradox. What happens to the information of an object after it falls into a black hole? General relativity says the information is gone forever, but quantum mechanics insists that information can never be truly destroyed. Reni entropy, the very quantity at the heart of this new universal law, is one of the most powerful tools theorists are using to tackle this paradox. A universal law governing that entropy could provide the missing link needed to finally resolve what happens at the edge of a black hole. And the exploration doesn't stop at the theoretical. Experimentalists are pushing the boundaries of entanglement into new, extreme territories. In a landmark achievement at the Large Hadron Collider, the world's most powerful particle accelerator, scientists at CERN recently observed quantum entanglement between top quarks. Top quarks are the heaviest known elementary particles, and seeing them entangled tests this spooky connection at energy levels higher than ever before. This opens an entirely new window to probe the relationship between entanglement and the standard model of particle physics. With a universal theory of entanglement in hand, physicists can now build a much stronger framework to interpret these extreme experiments and search for new physics beyond the standard model. Finally, let's touch on the most mind-bending idea of all. Some physicists have proposed a radical hypothesis that entanglement isn't just a phenomenon that happens within spacetime, but that entanglement might be what creates spacetime. The idea, often summarized by the equation ER equals EPR, suggests that two entangled particles, which appear to us to be separated by a vast distance, might actually be connected by a wormhole or an Einstein-Rosen bridge in the geometry of spacetime. From this perspective, the spooky action at a distance isn't spooky at all. The two particles are, in a deeper sense, the same object, connected through a higher dimensional reality. Our perception of distance between them is just a shadow of this deeper connection. While the work from Professor Kasuka's team deals with the dimensions of spacetime we know, not necessarily extra hidden ones, it provides a universal framework that any geometric theory of entanglement would ultimately need to align with. It sets a new, fundamental constraint on any theory that attempts to unify gravity and quantum mechanics. The discovery of a universal rule for quantum entanglement is a pivotal moment. It elevates spooky action from a perplexing paradox to a predictable, fundamental, and beautifully simple law of nature. While this breakthrough is, for now, a theoretical one, it provides a solid foundation and a clear roadmap for the experimentalists and engineers who are building the world of tomorrow. From the unimaginable energies of colliding top quarks at the LHC to the delicate quantum dance of qubits in a future computer, a single, unifying principle appears to hold everything together. The spooky action at a distance is looking a little less spooky, and a lot more like a law of the cosmos.